In this lecture, we're going to talk about singularities and ways of measuring how manipulable a robot is. In other words, we're going to assign a number to saying how dexterous, how useful a mechanism may be for a particular task. Recall that for a simple Jacobian, that's when the Jacobian was a square matrix, we were able to set the determinant of the Jacobian equal to 0 and then find out which joint angles satisfy this condition. Now really, we weren't looking at determinant equal to 0. We were really asking ourselves, when is the determinant full rank? And we had this rank question in mind because now we want to consider the question, what happens when the Jacobian is non-square? Now I remind you that we have this relationship amongst ranks where the rank of a matrix is equal to the rank of its transpose. In fact, the rank of a matrix is equal to notions of the rank of the square of the matrix, either J transpose J or JJ transpose. With this in mind, we have two conditions we can check to see when a matrix is not full rank. In this case, when we have more rows than columns, we check for singularities by examining the determinant of J transpose J. When the determinant of J transpose J equals 0, the joint angles are ones where that mechanism has a singularity. Likewise, if we have more columns than rows, then we check for singularities by examining the matrix JJ transpose. So when the determinant of JJ transpose equals to 0, those joint angles correspond to a singularity. Now, the pseudo-inverse that we used for the inverse differential kinematics only works when the Jacobian itself is full rank. What happens when it's not full rank? In other words, what happens when we are at a singularity, when either one of these conditions occurs? For that, we have an alternative means for constructing the pseudo-inverse, and it's based on something called the singular value decomposition. Now, before we talk about the singular value decomposition, let's just review some linear algebra. Again, we have a matrix that has m rows and n columns. We can think of this matrix as a mapping that eats n-dimensional vectors and produces m-dimensional vectors. In other words, the domain has n vectors, the range has m vectors. This notion of a null space are the set of vectors in the domain such that when they go through the mapping, you're at 0. In other words, these are vectors that have 0 in their range. Now, trivially, the 0 vector v lies in the null space of your matrix, but we're going to be interested in situations where your null space is non-trivial. It's not a point where there's actually many vectors in the null space. Finally, we have this nice condition here where the dimension of the null space of a matrix plus the dimension of the range of the matrix is equal to the dimension of the domain of that matrix. In other words, all the vectors into which you map to some non-zero amount plus all the vectors that map to a 0 amount equals the dimension of your domain. So let's discuss eigenvalues and eigenvectors very briefly. Now, I want you to look at this line here, and on this line we have a vector v. Now there are, for a square matrix, you can imagine that sometimes there are vectors when mapped through your square matrix just give you a vector along that straight line. In other words, the mapping scales the matrix. It could either lengthen it, it could flip it around going the other way, or shorten it. No matter what we do for putting a vector into this A map, we always get a vector along this line. And this happens sometimes. The condition for which this happens is we have our vector v mapped through A is equal to some scaling of the vector, original vector v, where lambda is some scalar. That's the scaling factor. What we'll do is we'll bring lambda to the other side, so we have this expression av minus lambda v equals 0. And then we'll pull the v out where we have this matrix a minus I lambda v equals 0. At this point, what we'll do is to find values of lambda where this expression is true, in other words, different scaling vectors, we're going to look at the determinant of this matrix here. Because for non-zero vectors v, this vector here, this matrix here has to be singular, and therefore its determinant has to be equal to 0. So the eigenvalues are going to be the lambdas for which this expression is true. It's the roots of a polynomial that's formed by this expression, and again, you can think of it as the scaling factor for v. Now note that there are going to be multiple eigenvalues, multiple scaling factors, so for each eigenvalue, there will be an associated eigenvector. The eigenvector is the basis of this space where the scaling occurs. Now if you look carefully at this expression here, you have a matrix times a vector that's non-zero equals v. So really you could think of the eigenvector as a basis vector of the null space of this matrix. And that's what we have here. The basis vector of the null space of A minus the identity matrix eigenvalue I is the eigenvector. You can also think of it as the basis vector of this invariant manifold. So let's do an example. Here's a square matrix A. To compute the characteristic matrix, or the characteristic polynomial, A minus lambda I, we take its determinant. So we subtract lambda from the diagonal elements, set it equal to 0. And since this is a 3 by 3 matrix, we have a cubic polynomial whose solution has these three roots, 1, 2, and 11. So 1, 2, and 11 are the scaling factors for the three different spaces for which we're going to be scaling our vector. Obviously, for the eigenvector associated with lambda equals 1, AV will just be equal to v, because lambda is equal to 1. So to compute what the actual eigenvectors are, we have to remind ourselves again that these eigenvectors are indeed the basis vector of the null space of this matrix. So by inspection here, it's pretty easy to see that x is going to have to be equal to 0, because x, the first row of that equation, makes x equal to 0. And then the only way to satisfy the next two equations is if there is a ratio of -1 to 2 to z and y. Now, we could have this be -10 and 20. That would give us a basis vector in the same null space. In fact, this could be -2, and this could be +1. Now let's look at let's hunt for the eigenvector associated with lambda equals to 2. Here's what the matrix looks like. Now, x can really be anything we want because this is a row of zeros. We choose 1 just out of convenience. The only way for y and z to satisfy these two constraints is that they be 0. So the eigenvector associated with lambda equals 2 is simply the x-axis. Finally, for the last eigenvalue, where lambda is equal to 11, here's the matrix, here's the basis, here's the vector for which we're trying to determine the null space vector. And once again, it's very easy to see that x has to be equal to 0, and the only way for y and z to satisfy these two constraints is when there's a 1 to 2 ratio between them. In fact, here, if you want, you can have these as being -1 and -2 as well. This can always vary by a scaling factor. So these three vectors are the basis vectors corresponding to the null spaces of the eigenvalues as such. So now, how does this generalize to non-square matrices? So we're going to consider first the case where A is an m by n matrix where we have more columns than rows. Here, we'll do is we'll construct AA transpose, which will be a square m by m matrix. With this square matrix has eigenvalues. Again, the eigenvalues and eigenvectors only apply to square matrices. So using the techniques we just described, we can hunt for the eigenvalues and eigenvectors of this square matrix. And then the singular values of A are simply going to be the square root of the eigenvalues of AA transpose. Just as we have singular values, we also have singular vectors, except we're now going to have left singular vectors and right singular vectors. Simply put, the left singular vectors are we're going to use those to form a matrix U, column by column, and the columns are going to be the eigenvectors of AA transpose. Likewise, the right singular vectors, we're going to use those to form a matrix V, and those eigenvectors are the eigenvectors associated with A transpose A. So now with V and U as well as our singular values defined, we're able to define the singular value decomposition. Given a matrix A, we can decompose it into this U, this was the left singular vectors, sigma, this will be a diagonal matrix whose diagonal elements are the singular values, and then V transpose, where the columns of V are the right singular vectors. It's worth noting that U and V are both orthogonal matrices of the appropriate dimensions. Now in the case where n is bigger than m, that's the case we're talking about, this sigma matrix, okay, of course has the same size as A, but here the number of columns is bigger than the number of rows, so the singular values will form a diagonal matrix, and once we get to the bottom, we'll have just extra columns of rows to fill out this matrix. So now let's look at the singular value decomposition when the A matrix has more rows than columns, n is less than m. Here we're going to construct A transpose A, and the game follows similarly. We'll look for the eigenvectors and eigenvalues associated with A transpose A. The eigenvalue, so the singular values, of course, will be the square root of the eigenvalues, and then the left and right singular vectors are computed exactly in the same way, and the result is a singular value decomposition that looks like the other one. The only difference is this sigma matrix is now going to be diagonal all the way to the rightmost column, and then we have the additional rows to fill out the matrix, so it's the same size as the original A matrix. The intuition for the singular value decomposition is like this. Let's say we start with a circle whose x-axis points to the right and y-axis points up. V transpose is an orthogonal matrix. It's going to be a rotation matrix, and all it's going to do is just rotate our circle. Now the sigma is going to tell us along each original dimension, so let's say the x direction and the y dimension, that we're going to scale this circle. So when we scale this circle, we form an ellipse. Here we scaled one radius of the circle to be larger, the other radius to be smaller. Now we're going to map this ellipse through an orthogonal matrix U, and that rotates the ellipse, and this gives us the final transformation. In other words, the matrix goes from this circle all the way to this ellipse. So now let's see how we can use the singular value decomposition to compute the pseudo-inverse. Again, here's our Jacobian. We know it's not full rank. So we compute the singular value decomposition. Here we'll have an m by m square orthogonal matrix, an m by n, same size as Jacobian, diagonal element of singular values, and then an n by n rotation matrix. Transpose is still a rotation matrix. The pseudo-inverse now has this form here. We simply transpose and invert the diagonal elements of the sigma matrix, and then we just reverse the order of the U and V, keeping the transpose over here. So now, for conditions where we have a non-square Jacobian that's not full rank, we're able to compute the inverse differential kinematics by using this pseudo-inverse. Likewise, there's the other pseudo-inverse for when the number of rows are bigger than the number of columns. Here we did number of columns bigger than the number of rows. In other words, n was bigger than m in this case.